Value stream mapping. The process of constructing a value stream map should be viewed as an extremely liberating experience for a manufacturing organization because it demonstrates the interconnectedness of all the various processes and functionalities associated with the effective production of a bioproduct. Value stream mapping allows a full build-out of each area's requirements related to the product production process in terms of what's required and when, and how this relates to obtaining a smooth flow and effective completion. The initial part of a value stream map will involve the description of the current as-is state. Why is this? This provides a detailed picture of the present practices and will be the starting point for analysis to determine the routes or path forward as improvements are made. The second feature of the value stream process is to determine the future or desired state, sometimes called the ideal or future or to-be state. This represents the new incarnation of the process which is desired in an ideal scenario where the process waste is removed and all other aspects are optimized to produce an effective lean process that is both efficient and provides value for the customer and the operating company. The key point in constructing the desired state scenario is to focus on constructing a process where the various operations add value. The mechanism involved. Being numerically based, it is by definition a fact-oriented mechanism that can stand objective scrutiny and is not subjective or opinion-based. The idea behind value stream mapping is to provide a visual pictorial representation of what is going on, supported by numerical analysis in order to enable others to evaluate performance. Through the use of value stream mapping, it is possible to determine where processes are adding value and where others cause bottlenecks and detract from the process of satisfying the customer requirements. The purpose of value stream mapping. The purpose of the value stream map is to determine what the process will look like in its ideal state. This will be represented by the future state map. With no restrictions on compromises then, the future state should embody the design of the ultimate condition that is possible for your manufacturing process. Optimizing the value stream map is done by analyzing the map for waste wherever the flow is less than ideal or perfect. What does this really mean? This condition is one where there is no non-value added functions in the process and where there is no single unit operation obstructing smooth single piece flow. For biopharmaceutical processes, this is difficult to attain, but often huge gains can be made provided one is disciplined in one's approach. This discipline is one of the constantly questioning aspects of value stream mapping, where the validity of the process and the steps involved are analyzed to see whether they actually add value. By asking better questions, the non-value added functions can be identified and dissected out to produce immediate results. Looking at the current state through the use of value stream mapping, questioning the major steps from a customer perspective will provide the most benefit to those doing this type of analysis. Clearly understanding the relative customers rather than just the ultimate customer for the process greatly assists in this process. Biopharmaceutical processes are frequently complex and often have holding steps, in-process and analysis quality specifications that need to occur or be reached prior to further processing. Careful questioning of these functions for criticality and overall effectiveness can prove to be invaluable in delivering sources of non-value added savings. Often, variability in processes can be an additional source of waste and inefficiency, and some of these can be traced to the following. Issues with raw material quality such as potency, bioburden, or heavy metal contamination. Variable raw material supply if key components are sourced naturally from global suppliers. In these cases, it is possible that delays can occur due to the variable quality or viral contamination of some subcomponents. Another potential problem here is the lack of appropriate equipment maintenance and issues with mechanical seals in bioreactors, which can cause losses due to midstream culture contaminations. Similarly, poor utilities maintenance and operation, such as water for injection and clean steam, may be hampered by frequent bioburden stability issues. Equipment malfunctions, such as incomplete autoclave cycles, bioreactor failures, valve malfunctions, can also contribute to lack of efficiency and productivity. Contamination issues, such as cell transfers during scale-up, where bioreactor seals may have failed, or mistakes have occurred due to operator training, both of these can play a significant role in the ineffectiveness of lean productivity. Simple things like a loss of plant skill sets due to personnel turnover, which can cause an increase in deviations, the slow completion of work, poor work standards, possible lack of an inspection standard, or incomplete cleaning can result to additional areas where biopharmaceutical process can fall down. On the documentation side, poorly detailed batch records which provide insufficient clarity on key steps can cause variability to be introduced as staff interpret the instructions differently. Where deviations have occurred, inappropriate follow-up of kappa issues can also affect how fast and how efficiently and how compliantly a batch may be released by the quality assurance group. So let's look at the basic format of a value stream map. In terms of its operational architecture, all value stream maps flow from left to right, with the raw materials for the next step being transformed as it moves to the right. The map charts all the steps and unit operations that are part of the process and adds a time component to that pictorial representation, which numerically exposes where the process resources are being expended. This also provides a qualification of the operations occurring in your process in terms of both value added and non-value added aspects. The goal then, as one moves towards the desired state, is to reduce or completely eliminate as much of the non-value added functions as possible. As with any process map, it is the layout of the basic process flow that is being charted. However, in a value stream map, this will also include the definition of each step and each function in terms of whether it is adding or not adding value to the process. When doing this exercise, it is important to remember that this must always be viewed from the perspective of the upstream customer. This is very important so that there is no distortion of the perception. The final piece of the value stream map anatomy is the scoring card, where all the key and relevant information is collected and displayed for use in obtaining and describing the new desired state. During the review process and during any ongoing scorecard analysis, this will be a point of focus for metric information during the performance evaluation step. So what are some key components of the value stream map? In constructing a value stream map, it is important to identify several key components, namely, who is the process owner, 2, the team that will develop the map, and 3, the tools that will be required to gather and chart the information. Let's start with the process owner. For the ownership role, it is best to identify a project manager for that specific purpose, so they have complete focus on the role and will have the authority to drive the definition of the value stream map to clarity. As with other project management issues, by assigning this to someone who is not a line manager with production responsibilities, it is possible to assure that a truly objective look or interpretation is gained and that appropriate changes are made to produce the required or necessary results to meet the desired state objectives. The team should be constructed cross-functionally and incorporate members of all aspects of the production functionality. So this should include members from production, engineering, project management, quality assurance, quality control, IT, and in some cases human resources. Let's talk about some of the tools. The use of commercially available tools is often a convenient aid to electronically capture the process, which allows for convenient distribution between teams and other interested parties. Useful tools for value stream mapping include products found at several websites that are listed in the PowerPoint presentation. The most effective way to learn value stream mapping is to perform the process using a wall chart and post-it notes to chart the various operations and data that are part of your process. This is so that one gets a complete understanding and appreciation of the mechanisms involved, and so that one does not overlook areas that may at first blush appear unimportant. Members of the team. It is best for the process team to be composed of a cross-functional mix of capabilities. Why is this? This provides a basis to assure that each and every key point is covered and considered, and that appropriate relative weighting is provided for those same points and parameters. It's important to recognize that no one knows all the answers, so separate representation of disciplines is required to assure that you develop a complete and accurate picture. The cross-functional project team will focus on acting as a focus group, which will perform in an environment that is free of encumbrances and constraints of day-to-day job functional responsibilities. An important member of this new team is a facilitator that can lead the group and challenge ideas, beliefs, and perceived constraints that might be limiting to the ultimate goal of a new, efficient, lean value stream map. This role is best played by someone external to the team, such as a consultant, who is familiar with not only the tools that will be needed to be considered and used, but also the nuances of pharmaceutical manufacturing that require attention. This external facilitator can also mentor or act as a coach for lean practices in the way a sensei type program would operate. In terms of critical mass, it's advantageous to limit the size of the cross-functional team to one that provides sufficient expertise but which is not too large to be difficult to manage. Often 5 or 6 people led by an external knowledgeable facilitator provides a good sized group that will meet the needs of the value stream mapping exercise. So to recap, who are useful members of the cross-functional team for a value stream mapping program? These might include the process owner, who is responsible for the delivery of the biopharmaceutical product from the plant, the process engineers, who are charged with shaping the design and continued performance improvement of the plant, the operational staff that function in delivering the product through the operation of the process, the supply chain management for the procurement and integration of raw materials and supply elements that factor into the overall process. Quality control and quality assurance are needed to fully integrate the regulatory compliance requirements so that the product flows out of the facility in a smooth, leveled, consistent and compliant mechanism. Information management resources are also required to assure that the required data and documents arrive in parallel with the in-process work and the finished product. In this way then, we assure timely processing at the biopharmaceutical distribution centres and beyond as the product reaches the client. So what's the starting line? As the current state value stream map is developed, it will become apparent very quickly where the waste is. Furthermore, as an increasing level of detail is developed and understood, so much of the waste will be universal in its origin. The place to start a value stream map is at the end near the customer, so in most cases that might be at the warehouse or the distribution centre. From this starting point, the cross-functional team should identify the key steps involved in a stepwise fashion and then build out key scorecard data sets for each of these from the information being gathered. These box scores will act as the data repositories for the exercise. Let's talk about the process. The best way to properly evaluate how a process runs is to observe the process live and, where convenient, to videotape the key steps. Experience teaches that a live recording of what actually happens as the process is operated provides a truly honest representation of how things really run, and not how they are supposed to run or operate per some engineering flowchart. This is often referred to as doing a Gemba walk, where one goes out to the point of activity and observes things firsthand. By recording and charting the events live, it is possible to observe interference points as they occur and to see how they eventually lead to process bottlenecks. In addition, they provide an opportunity to highlight the fragility of certain operations and practices which are not readily apparent without a live observation. The key here is to map the true typical mode of operation so you have a clear understanding and appreciation of the current state scenario. Without an accurate version of this, there is no starting point to develop the transformation plan for the future state vision. So what's some of the important information to gather? It's important to gather as much relevant process information as possible, especially information and data that has a numerical component. Such information would invariably include, but not necessarily limited to, the following: lead time data, cycle time data, changeover data, personnel levels, maintenance time, individual process unit operations data, production specifications such as the acceptable quality limit, production targets, equipment operating capabilities, standard equipment performance, output of products, production history, performance, records and capability, operational availability, operational history and a reliability record, standard work schedules, shift mode and number of, available production window, quality related information such as deviation events, etc., testing capacity and performance records, inventory on hand, work in progress, number of batches needed for products, frequency of production for product campaigns, size of production batches, both bulk and finished goods, supply of raw materials, the time, quality, the control and the variability, costing information such as physical plant and buildings, infrastructure and administration, IT management overhead, equipment, operational costs and direct labour, indirect labour, utilities, raw materials, testing QC requirements and costings for quality assurance, warehouse and distribution costs and takt time. The tools. Several tools can be used to create and identify root cause in a value stream map. Some of these include the box score, debate charts, plan, do, check, act charts, Kaizen storyboards, fishbone and 5 whys analysis. As you review the process value stream map and plan your transition to the new future state situation, the project team identifies many sub-projects that will be needed in order to complete and effect a system change. Impact of this without proper management will be that the team will drown in the overwhelm of things that require attention. To overcome this, the team must take many small sub-projects out of the overall plan and break them down as part of the larger project plan. Now, using a triage or prioritization approach to the sub-projects, it is possible to develop a rational Kaizen continuous process that will be both manageable and focused. In developing these approaches, it is best to focus on the removal of one waste element at a time so you can achieve the goal. Kaizen continuous improvements through PDCA methodology is most successful when successive incremental gains are made as opposed to trying to solve everything through one all-encompassing change. The box score. The box score is a summary chart which records key performance measures for the process being studied. Typically, box scores will display total lead time and value-added and non-value-added times for that step. Other stats may include cycle time, takt time, changeover time, the number of pieces or the number of units per shift, scrap, and uptime. Focus of the exercise, it may be most beneficial to limit this information to prevent information overload, which would be confusing. An important point to stress here is that the lead times and the takt times set both the tone and the way for the overall process to be performed. Specifically, the lead time represents the amount of time that is required for an individual unit to travel through the overall process. Using DMAIC methodology, D refers to the definition of the problem in quantitative terms. For example, this could be X% increase in efficiency over Y months. M refers to the measurement of the data required to perform the ongoing analysis. This is the data that provides information about how to influence and change the manufacturing process. A refers to the analysis of the collected data using various statistical tools. The analysis phase determines whether the variances are random events or ones that have a pattern that can be affected by a methodical event change. I refers to improvements made to the process as a result of changes made possible through the analysis of the data sets. Finally, C refers to the control mechanisms that are established to maintain sustainable performance of the process through standardized collection and analysis of operational data. DMAIC has much in common with the PDCA cycle, first developed by Edward Deming, who laid the foundation for much of the modern approach to quality control. In lean methodology, this is presented as follows. Define, represented by D, this is the definition of the customer demand required, specifying the process lead time to meet that need. Measure, or M, this refers to the mapping of the process and the data flow involved in the process. Analysis, A, expresses in terms of process efficiency and numerical cycle qualification. Improve, I, recognizes the process flow patterns and eliminates the waste in the system. Control, C, develops mechanisms to appropriately design the workflow to avoid waste introduction or new problems due to these specification errors. Let's look at the PDCA cycle. This is the system methodology first defined by Edward Deming, similar to DMAIC, in that it infuses the lean concepts of continuous improvement, or Kaizen, into process manufacturing methodology. The operational methodology is broken down into 4 sections as follows. Plan refers to the identification of the things that will be changed during the Kaizen event. It also refers to the steps involved with the change. Do refers to the implementation of the plan in a test situation to see if the results occur as predicted. Check refers to the analysis phase where results of the change are reviewed, checked and verified to assure that the outcome is an improvement over the existing previous state. Act refers to the broader deployment of the plan and any revisions necessary to assure sustainable results. So let's look at Kaizen events. This is a focused activity where everyone in the work module is receiving attention. This often involves a complete PDCA cycle performed within 5 business days and focuses on removing all forms of waste and bottlenecks from the process to create maximum value. A key point that should be stressed about a Kaizen blitz and Kaizen events refers to the impact of the outcome relative to the cost expended. This should be very significant for very modest investment. This is very important. Often due to the highly compressed nature of these Kaizen blitz events, follow-up work involving monitoring and fine-tuning is continued after the main event is finished. Usually this should be factored in for completion within 30 days of the event to maximize the impact. In parallel terms, these events are usually undertaken by a cross-functional team. The team works to a timed work agenda, with the process being tracked using special documents referred to as a Kaizen storyboard. The first important step involves the definition of the problem to be resolved, and this is described in a current situation table. Next, one ideal solution is described in part of the table, together with the nice to have features to enhance the process. It could be easy access to a standard operating practice, for example, through an electronic terminal in the process area. Next, the target measures need to be identified so that it's possible to know when the solution meets the needs of the problem statement. These could be particular target yield metrics or unit operation cycle time targets. Following on from this, it is important to properly set out the process to be used to identify and brainstorm root causes for the problem and how solutions will be determined. This might involve the use of a fishbone analysis, for example, retraining, or new operating practices that will be required. The next chart should detail the results of the process and whether they meet the goals of the Kaizen event. Finally, assuming the target goals were met, a plan should be described which will ensure that the new measures and improvements are sustainable and that there is a measurement monitoring process in place to provide a mechanism for a long-term performance assurance. Important in the rollout is how the improvements are reduced to working standard practices, how appropriate metrics will be used, and where possible, how visual controls can be used to enhance the rollout of the plan. Kaizen events are challenging to perform, so when the exercise is complete, it is very important to celebrate the successes achieved to provide the momentum for the next round of continuous improvements. This celebration should involve everyone in the team. So let's look at fishbone analysis. Determining what actually caused the problem can be a really lengthy and involved exercise. Often, due to a very significant number of interactive issues, the discovery of the true cause of the problem may be almost impossible. With that said, however, one very powerful and helpful technique is to use a fishbone diagram, often referred to as an Ishikawa diagram. This can be used to pinpoint potential root cause suspects from the plethora of contributing things that may confuse or mask the true underlying reason why something is not working properly. This is a general guideline of categories that often produce useful outcomes, although this can change and is not necessarily a hard and fast rule. Using this approach, the project team develops a list of reasons for the root cause of the problem in a brainstorming exercise. Through asking sequential questions, additional bones are added to the fish structure for each sub-reason until a potential reason for the root cause is identified. At this point, these reasons are identified through the drawing of a cloud on the fishbone around the reason which identifies an opportunity for a Kaizen event.